Hello everybody who is interested in my presentation. Thank you for your attention, and my name is Margarita Ilyasova, and I would like to share with you our achievements in measurements of neutron fluxes from tokamak plasma using a compact neutron spectrometer. So neutron spectrometry, and especially use of compact neutron spectrometers based on scintillators, is an effective tool for plasma diagnostics and provides such measurements as neutron wield, fusion rate, fast ion confinement, energy, and spatial distribution of neutrons and fast ions. In tokamak Tuman 3M, the discharges with injection of neutral deuterium beam and deuterium plasma were studied, and in these discharges, deuterium plasma with 2.45 MeV neutrons production occurred. In these neutron measurements on the Tuman 3M, we used a neutron spectrometer based on BC501A scintillator, which was installed in Tuman 3M tokamak hall. The parameters of Tuman 3M are presented in the center of the slide, and the arrangement of the spectrometer in the tokamak hall is presented in the left picture. The spectrometer had a tangential line of sight and was shielded from magnetic field and had X-ray fluxes. The spectrometer was connected with a high voltage supply and transient digitizer, which processed the signal from the spectrometer with sampling rate of 500 MHz. The first question is the neutron gamma separation, because BC501A scintillator detects end-neutrons and gamma quanta. And signal corresponding to neutrons differs from signal corresponding to gamma quanta, and the difference is shown in the picture. So the difference is in the tail part of signal, and each single event, the pulse of each single event can be fitted by the exponential formula presented in the center of the slide. And obviously, the pulse shape corresponding to neutrons differs from pulse shape corresponding to gamma signal. So the pulse shapes are presented in the picture on the slide. So this difference provides neutron gamma separation by pulse shape, which is implemented in the Degasson code. The Degasson code was developed at the Institute, and the procedure of pulse shape fitting is described in details in these two articles. And neutron gamma separation by pulse shape, which has an advantage in comparison with standard charge comparison separation method, is described in this article. So after neutron gamma separation, we obtain a pure neutron energy spectrum, which is described by integral convolution, which is presented in a slide. And the integral convolution includes neutron distribution function and the detector response function. So to obtain neutron energy distribution, we need the detector responses, which were measured in the experiment on the cyclotron of Yoff Institute for our neutron spectrometer based on BC501A scintillator, and the experiment is described in this work, and set of obtained responses is presented in the center of the slide. And also in these measurements, the neutron registration efficiency of the spectrometer was also measured as a function of neutron energy and presented in the picture. So these methods and responses were applied for neutron measurements on the 3M tokamak in the discharges with deuterium beam injection, and the parameters of one of the studied discharges are presented in the left picture on the slide, and in the picture E there are a counting rate of the neutron spectrometer during the beam injection. So the signal of beam injection is in the picture D. The counting rate signal corresponds to only neutron events after neutron gamma separation, and the gamma fraction after neutron gamma separation of the signal is presented in the picture F. And corresponds to registration of hard X-ray radiation during the plasma discharge. After neutron gamma separation, the neutron energy spectrum was obtained, the black line in the central picture, and from the measured neutron spectrum, the neutron distribution energy distribution was reconstructed, the blue line, and in the distribution there are 2.45 MeV energy peak corresponds to unscattered neutrons from deuterium reaction. So the reconstruction of neutron energy distribution gives us so-called deconvolution coefficient or reconstruction coefficient, which is the ratio between number of unscattered 2.45 MeV neutrons, that is the integral under the peak, to the number of all registered neutron events. So this is the integral under the whole neutron spectrum, and this coefficient gives us the estimation of number of unscattered neutrons in any time interval, and the number of unscattered neutrons divided to probability of neutron hit the spectrometer volume and normalized to the chosen time interval gives us an estimation of fusion rate. So this relation was used, and we estimated deuterium fusion rate in one of the discharges, so the time evolution of fusion rate with time step of half of millisecond, and the probability was measured, was calculated using MC&P6 code. So this is the Monte Carlo calculations. Another thing that is studied in neutron measurements on tokamak 213M is deuterium ions confinement. After the end of beam injection, blue line, we can observe a slowing down of neutron spectrometer counting rate. The slowing down can be fitted by the exponent with characteristics decay time. The decay time has two contributions. The first one is slowing down time due to Coulomb interaction, and the second contribution is determined by the deuterium ions losses due to charge exchange processes and beam instabilities. So the first decay time can be estimated from experimental measurements and is about 1.88 milliseconds. The second term can be calculated from plasma parameters, and the formulas for the calculations are given, for example, in this work. And from the first relation, we can find time of deuterium ions losses, which is about 14 milliseconds for the studied discharge, and these estimations give us a conclusion that the main processes with fast deuterium ions in this discharge are Coulomb interactions. So this is it. This is our achievements in neutron measurements, and the use of BC501A compact neutron spectrometer gives the neutron wield measurements, the deuterium fusion rate estimation, the estimation of neutron flux decay time, the study of the deuterium ion confinement time. And also we demonstrated that the neutron compact spectrometer can be used as hard X-ray flux monitor. So this is it. Thank you for watching. Thank you for your attention.